video we're going to talk about titrations. Titrations is a common lab procedure where we have a very accurate, we call this a burette. It's got accurate gradations. We can get good volume readings on our burette. And then I'm going to put a known solution in here frequently. In fact, what we're going to talk about is I'm going to put a known strong base in the burette. I'm going to put some sort of unknown weak acid in this flask. And what I can do is I can add very slowly, drop by drop, I can add a very precise amount of the base to the acid. And I can add a little bit at a time and make some measurements. But it is a very controlled way. We can use this for acid bases. We can use this for redox reactions. We can use it for a lot of different applications. For now, we'll talk about acid-base titrations, but it is a way to add a precise amount of a substance in a controlled rate and make measurements to determine something about the unknown. So here's our titration setup. I've got a burette here, and I filled it with some sort of known solution with a known concentration. I want to look at weak acid strong base titrations. There's many different ways to do titrations, but this is one of the most common. So what I'm going to do is in my burette I'm going to put a known solution with a known precisely measured concentration. Let's, for example, say I've got sodium hydroxide solution and I've standardized it, measured it out to 0.100 molar concentration. So I know exactly what's in there. I know the molarity to a very precise level. Therefore, I can calculate the amount of sodium hydroxide I'm adding by saying, well, the molarity times the volume equals the moles added. In my unknown, I'm going to put some sort of unknown solution of a weak acid. So I'll put a weak acid HA. Now what might be unknown about this acid, maybe the concentration is unknown. Maybe I've got a mixture and I'm trying to find out how much HA is in there. Maybe I don't even know what acid is. I know I've got some kind of weak acid, but I'm trying to find the identity of this acid. So I put my unknown in here. I'm going to add a hydroxide slowly, tracking my volume so I know exactly how much hydroxide I'm adding, and I'm going to look for some things to happen in my flask. So what we're going to do with this titration is we're going to plot what happens to pH over as I add hydroxide. Notice what I had in there was sodium hydroxide. The Na plus is a spectator, so we're going to look at the net ionic situation. So we're not going to really worry about, yes, it's the hydroxide that's part of the reaction that's happening. The sodium is a spectator. So it's a weak acid. Let's say if the pH is 2, it's going to pH a little bit above 2. Let's say we start there. What do I have to begin with? I haven't added any hydroxide, so the volume added is 0. What I have at this initial point is a solution of a weak acid in water. I have an equilibrium situation of a weak acid in water. What does that do? To some degree, it creates the hydronium ion and the conjugate base. So what's going on here, I could find the pH here if I knew the amount, or if I know the pH, of course I can find the amount. But I've got a weak acid solution in water, so what do I have to begin with? At this first initial point, I've got a solution of the weak acid. By definition, this weak acid is going to have very little of this created. So 99%, or approximately 99%, will be the weak acid, and around 1% will be the conjugate base. So it's almost all weak acid. Yes, a little bit has ionized to form the conjugate base, but I've got a solution of the weak acid in water. If I look at the particle diagram, of course exaggerated. So what do I have? I have mostly the weak acid. This would be the conjugate base. I've omitted the water molecules. I have almost all weak acid and very small amount. Of course, I would have to draw 99 more of these things. But I've got only a very small amount broken up. I have almost all weak acid, very, very little conjugate base to begin with. And I can find things and do some calculations with this equilibrium situation. In a titration, we have two things going on. Because what I'm going to do now is I'm going to start to add a strong base to this solution. And so I have two things going on. I have an equilibrium situation of my weak acid in water, a weak acid solution. Now I'm going to disturb my equilibrium by adding a strong base. This is not an equilibrium situation because I have an acid and a strong base. Therefore, that will react until something is consumed. So this one is not an equilibrium. This is disturbing my weak acid equilibrium by adding a base to make the conjugate base. So what's happening as I'm doing this is I'm taking that weak acid and converting some to the conjugate base. So I come along here and I've added some hydroxide. I've taken a chunk of that initial weak acid, converted it to the conjugate base. So what's going to happen is my pH is going to rise slowly. But notice what I have. What I now have created, I took my initial weak acid solution and I have turned it into a mixture with significant amounts of weak acid and conjugate base. I have a buffer. So I have developed this buffer along in here. So the pH is going to rise slightly because I am adding a base, but because of the presence of the weak acid, significant amounts of the weak acid, the pH will remain fairly stable as I go along. I'm going to continue to add base, so I'm going to add more. I'm going to add some more hydroxide. I'm going to take more of this. I'm going to turn it to the conjugate base. I'm going to check it a little bit later. And I'm continuing this process. Now my amount of weak acid has dropped. I still have a significant amount. I'm getting more conjugate base, but I'm still in that buffer range. So I go for a ways. As long as I have a significant amount of the weak acid present, of course I'm using it up as I go along in my titration. I'm using it up this way, creating this. But as long as I have a significant amount of that, I will have a stable pH. In this range, I have a buffer. Now we get to the point where the moles initial when I get to the point where the moles that I started with, the moles of the weak acid that I have initially is equals. The moles added. So now when I get to that point, I'm right at that point where all of the weak acid I had has been consumed by the hydroxide. What do I have? These are now consumed. I have a solution of the conjugate base. At that point, remember, for a buffer to occur, I need significant amounts of the weak acid and the conjugate base. I need enough of both. When I start to run out of this, when I get down to where I've almost run out of this, I no longer have a buffer. It's no longer stable. I see my pH spike up, and then of course I'll just have excess, and I get this titration curve. This point, the middle of the spike, is called the equivalence point. So at the equivalence point, I have got to that point where whatever moles I had here initially, I have added the identical number of moles of hydroxide. I have turned this into a solution of the conjugate base. All of that HA that I started with has been consumed, except of course for the very small amount that will be created in equilibrium, and it's been converted into the conjugate base. How do I write the chemical equation for a solution of the conjugate base? Here's my solution for a weak base in water. I create the conjugate acid, which is my original weak acid, and hydroxide. So notice that what I have here now is I have a solution of a weak base, therefore the pH of this is now going to be above 7. So my equivalence point is going to have a pH somewhere above 7 because this is, at the equivalence point, a solution of a weak base. In our next video for titration, we're going to look at more details. What are some significant points of this titration, and what kind of things can we calculate? What kind of unknown situations can we find about our weak acid solution?